Hello, my name is Henrique Gouveia. I'm a postdoctoral researcher in the graduate program in nutrition at the Federal University of Pernambuco in Brazil. And during my PhD, I had the opportunity to spend some time in Morelia, in Mexico, in the state of Michoacán. And today, I'm pleased to share some insights from my research, which focused on evaluating the effects of creatine supplementation in an experimental model of cerebral palsy. But before presenting the results, I will talk a bit about creatine and introduce cerebral palsy to you. So, creatine is a natural compound found primarily in skeletal muscle, though it's also present in smaller amounts in brain, kidneys, liver, and testes. Our body can produce creatine through process in liver, kidneys, and pancreas, but this production is limited to about 1 gram per day. This synthesis requires the amino acids glycine, arginine, and methionine, and additionally, creatine can be obtained from animal-based foods. It was first discovered by the French chemist Michel-Eugène Chevreul, and in the 1970s, creatine was primarily used as an ergogenic aid to enhance athletic performance. However, from the 1990s onward, research, let's say, expanded to explore its broader potential. As I mentioned regarding creatine intake from food sources, here's a table with some examples, and it's commonly accepted that a loading phase of 5 grams taken 4 times daily for 5 to 7 days can increase muscle creatine and phosphocreatine levels by about 20 to 40%. And after this phase, continue with 3 to 5 grams per day helps to maintain these elevated levels. So as you can see, achieving this level of creatine through diet would be challenging, which makes supplementation necessary in most cases. Within the cell, the primary and earliest known role of creatine is in the ATP-CP system, part of anaerobic metabolism, and the mechanism is straightforward, where phosphocreatine donates a phosphate group to regenerate ATP from ADP. So, among all the biochemical pathways that synthesize ATP, the creatine phosphocreatine system is the fastest at replenishing ATP, making it essential in conditions where oxygen is limited. Regarding the mechanisms of the action of creatine, if you start by examining its peripheral mechanisms, several possibilities emerge. And the first mechanism involves water retention, which is considered an obligatory effect because creatine naturally retains water upon entering the cell. And this regulation of intracellular volume can lead to changes in gene expression and regulatory factors that may activate the proliferation of satellite cells, which are involved in myofibrillar protein synthesis. Additionally, this activation of protein synthesis may occur directly by creatine effects on IGF-1, for example, or for a BP1. And the resulting increase in protein synthesis can enhance muscle volume and strength, which can be also influenced directly by the creatine's role in the ATP-CP system, as we saw before. And this increase in strength may further stimulate myogenic factors and proteins like mTOR, creating, let's say, a reinforcing cycle. And finally, creatine interacts with AMPK protein and consequently with GLUT4, facilitating glucose uptake into the cell. So this array of effects show that creatine's benefits extend beyond sports performance, proving useful in conditions involving reduced muscle mass and strength, such as cerebral palsy, the focus of my study. And creatine also impacts oxidative stress, both indirectly through membrane stabilization and enhanced energy capacity, and directly through antioxidant effects. Compared to skeletal muscle, only a small percentage of total body creatine is found in the brain, less than 5%. However, this small amount plays a crucial role in brain energy production. Creatine supplementation supports a more consistent regeneration of ATP in the brain, particularly in situations such as accelerated ATP turnover during complex cognitive tasks and impaired ATP turnover, as in conditions such as hypoxia, sleep deprivation, and various neurological disorders. And under these circumstances, creatine is associated with enhanced neuronal activity. Now, let me introduce the creatine study conducted by our research group, which was published in Nutrition and Neuroscience, and also included the collaboration of Mexican researchers such as Angélica Roque, Luis Torné, and Omar Guzman Quevedo. And before summarizing the results we obtained, let's first discuss what cerebral palsy is. So it's important to understand that mammals experience periods during the development of physiological systems when they are particularly vulnerable to environmental factors. And these changes can disrupt system activity and may lead to development of conditions such as cerebral palsy. So cerebral palsy is a neurological disorder characterized by abnormalities in movement, body posture, and muscle tone. Is a static and non-progressive condition that can occur prenatally, perinatally, and postnatally up until the second year of life. And it's the most common cause of chronic motor dysfunction in childhood. So cerebral palsy is associated with movement abnormalities, movement disorders, muscle atrophy and weakness, and spasticity, which is involuntary contractions that is found in 80% of the cases. Additionally, lesions in white and gray matter, as well as moderate to severe sensorimotor disturbances and behavioral or cognitive deficits are also observed in this condition. Furthermore, some studies have shown alterations in inflammatory markers in individuals with cerebral palsy, linking these changes to neurological deficits. And to study cerebral palsy, experimental models using Wistar rats have been developed, and over the years, various alterations similar to those observed in humans have been documented in these models, including changes in showing muscles, growth rate, and muscle strength, and cortical organization. While several models exist, we utilize one characterized by the combination of postnatal anoxia and sensorimotor restriction, which is the primary cause of the motor impairments observed in this condition. So in the creatine supplementation study, we administered creatine at a dose of 300 milligrams per kilogram per day, initially through Gouveia and later mixed with water to the animals with cerebral palsy, starting from postnatal day 21 until they reach P60. We assessed developmental parameters such as body weight and food intake, muscle strength, and locomotion. And after collecting the samples from the hippocampus, we evaluated the expression of inflammatory markers such as interleukin-6, interleukin-1 beta, and TNF-alpha, as well the density of microglia and the percentage of activation of the cells, which are involved in immune response, and an increase in the number of the cells, the microglia, along with the activation, is associated with an exaggerated inflammatory process that can lead to damage to the central nervous system. So initially, we observed a reduction in body weight and weight gain due to cerebral palsy throughout the study period, while creatine supplementation led to an increase in body weight up to day 50. And the reduction caused by cerebral palsy expected, given the motor damage and the muscle atrophy resulting from decreased movement, as well the deficits in sucking and chewing movements, with impairs the food consumption. And in contrast, creatine appears to play a beneficial role. We also observed a decrease in food consumption and muscle strength associated with cerebral palsy, while creatine supplementation resulted in increase in both. However, the effect was not consistent because it was only seen on P60 on food consumption and P30 on muscle strength. Here are the results of creatine supplementation in control animals. So in CP animals, the animals with cerebral palsy, it was only seen on P60 in food intake and P30 on strength. So the effect, as I said, was not consistent. And the reduction in food consumption in cerebral palsy is something expected and can be associated with the reduction in muscular muscle mass and decrease in oxidative fibers. And with relation to creatine effect, although some studies suggest a possible impact of creatine on food regulation, more research is needed to explore this aspect of creatine concentration and regulation of food intake in more detail. In addition, we examined the effects of cerebral palsy and creatine on parameters such as food contact area and contact intensity. And there was a reduction in both parameters in the short and long term, while creatine supplementation reduced the damage at P30 on food contact area and on P60 on food contact intensity. And the negative effects of cerebral palsy are associated with muscle fiber atrophy, joint and knee degeneration, and severe gait and posture impairments. While the positive effect of creatine supplementation may be associated with the mechanisms we saw early, and this applies to the results of body weight, muscle strength, and locomotion. But other studies have been published evaluating the effects of creatine, such as the one by Aoki, in which the creatine supplementation reduced immobilization-induced muscle loss after continuous supplementation for 14 days in rats with 5 grams per kilogram per day. And after 14 days of creatine loading, the total creatine content in soleus and gastrocnemial muscle increased by 25 to 18% respectively, attenuating the muscle loss. And the authors concluding that this effect may be associated with the ability of creatine to induce a mitotic effect in satellite cells, as well as to protect the skeletal muscle cell against proteolysis. That was something that we saw on that image before. Or the one by Mazuka Nasser, where after supplementation for around 5 days, also with 5 grams per kilogram per day, they reported a slight attenuation of mass loss in soleus and extensor digitorio longus, muscles of rats subjected to high limb immobilization, as our study did. However, supplementation was unable to attenuate the reduction in muscle cross-section area and decrease in muscle strength, probably because of the only 5 days of supplementation, which was not chronic supplementation. And finally, we investigated the density and percentage of activated microglia in the hills of the hippocampal dentate gyrus. And while cerebral palsy resulted in an increase microglial density and a higher percentage of activation, indicate a possible rise in inflammation in the hippocampus, creatine did not affect microglial density. However, creatine supplementation did prevent an excessive increase in the expression of pro-inflammatory cytokine interleukin 6. However, there was no difference between the groups in the interleukin 1 beta and TNF alpha. Other studies have also reported positive central effects of creatine supplementation. While no other study has specifically evaluated the impact of creatine on microglia profile, as our study did, several have examined parameters associated with neurogenesis. For instance, a study by Lin found that after 4 weeks of chronic mild stress, there was a decrease in the number of Ki-67, a marker of proliferation, and DCX, a marker of differentiation, in the hippocampal dentate gyrus, and this decrease was reversed by creatine supplementation through activation of this pathway. And another relevant study by Mao investigated the neurocognitive effects of oral creatine supplementation in young female rats with lipopolysaccharide-induced cognitive impairments, which mimics the human mild cognitive impairment. And this study demonstrated that creatine supplementation improved spatial learning and alleviated the LPS-induced memory deficits, as well as recognition memory deficits. And additionally, it increased mTOR-C1 signaling and enhanced synaptogenesis in the dentate gyrus, a region that is critical for hippocampal dependent learning and memory. So these studies are significant in demonstrating the positive effects of creatine on central nervous system. So in this image, we have a summary of the study, of our study. So we observed the expected behavior of a healthy brain, more specifically the hippocampus, characterized by stable microglial density and activation percentage. In contrast, the hippocampus of animals with cerebral palsy showed an increase in both microglial density and activation percentage. And notably, these parameters were not altered by creatine supplementation. However, as we saw, creatine did reduce the elevated levels of inflammatory marker interleukin 6 found in cerebral palsy animals. And additionally, creatine supplementation led to improvements in abnormal body weight development, as well as observed alterations in muscle strength and locomotion. And finally, as I mentioned at the beginning, part of this study was conducted in Mexico, specifically in the city of Morelia, in the state of Michoacan. And during this time, I received invaluable support from Dr. Luz Torné and Dr. Omar Guzman Quevedo. And below is a photo of my research group from the Department of Nutrition at the Federal University of Pernambuco, in the state of Pernambuco, in the city of Recife, where I'm pictured here with my advisor, Dr. Raul Magalhães de Castro. And I would also like to express my gratitude to the organizing committee of this event for the invitation. And here are the references I used for this talk. And I would also like to thank you for your attention.